Was wird daraus, wenn der Bruno mal tot geht? Wo landen diese Sachen? Wo landen diese Instrumente? Was wird daraus?
Hi everyone. Hope everyone's having a good reading week. Right? Welcome to today's workshop. Damn, Teddy. Go ahead.
Hi guys, I'm your Jira Christina. This is my first workshop, so be nice to me, alright?
Sadly, we had to move this workshop online, but hopefully that's not an inconvenience rather than more of a convenience for you guys, right? And hopefully we can give you a good workshop.
So I'll put the attendance form here while you guys trying to fill it in. Yeah. So today I'll go over the outline, and then I'm going to do the first part of our workshop, and Fam is gonna finishing it up with modern cryptography. Ooh, exciting! Yep. So let me know when you finish, and then we can move on. I also need to get myself signed up here because we need to take attendance. So attendance allows you to vote at our year-end meeting, and also gives us the number of people attending our workshop, so we can report to our sponsors and get more monetary prize for you guys. All the money came through sponsor, either went to maintenance of the infrastructure or it went to your monetary prize as a CTF. So make sure you fill in this attendance form so you can get more. You're more likely to get a prize in our CTF. Good. Okay, so let's move on. I'll try to post this attendance sheet at the very end if you haven't filled it in yet. And so today's outline. So we're going to start off with some terminologies, data representation, and I'll get you guys into classical ciphers. This will be a short introduction to classical cipher. There's many out there, so if you guys are interested, go online, search it up. It's really fun. I hope you guys enjoy it. And then Fam is going to introduce you guys into modern cryptography, and then we'll be finishing off after Fam done his presentation. So terminologies, encrypt. So when we encrypt something, we are turning something that's recognizable into something that's not recognizable. And decrypt is just undoing the encryption. So we turn something that's not unrecognizable and then turn it back to what is recognizable. I hope this makes sense. And then cipher is what. Let's start from plaintext. Plaintext is the message you want to send in plain without any modification. And then cipher is when you encrypt plaintext. So you make plaintext into something that's not directly recognizable. Hope that makes sense. Any questions? If you have any questions, just put it in the chat. I'll try to check it from Fam's screen. And key is a media used for encryption or decryption. Basically, use a key. Well, we'll get to that later. So just remember, it's sometimes a part of encryption, but not always. And then algorithm is just a series of steps. And we'll get to all of this later. So don't worry if you don't understand right now. And looks like there's no questions. That's good. Okay. So I'm moving on. If you have any question, leave in the chat. I'll try to come back later. Data representations. So data have different representations. So usually what we see is in ASCII, or ASCII is only part of what you see. If you're not speaking English, then something you see is usually like in Unicode, I believe. But ASCII is like your classical letters and numbers, and there are some symbols that's also represented in ASCII. Actually, I can probably search up ASCII table if it's not too hard to search up. So here. Okay, because I can do load. So this is an ASCII table. You can see everything on there can be represented in different formats, such as decimal, hexadecimal, octal. That's what we use. Like hexadecimal is what we use often in in system, I believe, in binary. And then decimal would be useful if you want to code. For example, if you want to say change, like find age quickly, you can use the ASCII value of 104 and then convert it to like the ASCII for. I'm not sure what I'm talking about, but that's kind of, hopefully that makes sense. And then there's also binary, which is ones and zeros. I believe most of you guys probably heard of it. And base 64. So this one is something that we encounter a lot during CTF. So watch out for this equal signs where it just seems like capital letters combined with numbers that's likely to be a base. Yeah, so what you see right here is just different representation of cryptography. It's fun. Next topic. Tell me if I'm going too fast. So substitution cipher is if you replace is represent one letter or a block of letters using other letters or block of letters. Thinking of substitution in math, that's kind of the idea, like substitute this into this. So our classical substitution cipher is Caesar cipher. Caesar cipher is done by shifting the text by a certain amount according to the order in alphabetical table. For example, if you want to shift Z 3 places to the right, then you would go from Z and then because there's no letters after, you go to the start, so A and then B and C, so Z would correspond to C after shifting left 3 place. Yes. So what you can see right here is shift one letter to the right, turning cryptography is on to this unrecognizable text. But something you can notice is there's still space and like everything, like just the letter got shifted, but the space is still there. So usually for these types of cipher, we can just brute force every possible solution, or we can use frequency analysis method if there's a lot of text available for us to decrypt the message.
Explain those.
So frequency analysis is because like in English, when you say a word, usually there's like some letters show up more frequently than other letters. So by looking at the frequency of a specific letter showing up, you can kind of guess which letter it is, or if you know like the beginning of the letter at first, then you can figure out what this letter is substituting for, if that makes sense. Please let me know if there's any questions, if I'm not explaining clear enough, need more further explanation. Looks like no questions. So I'm moving on. So here's your first challenge. I'll give you maybe 5 minutes to do this. So try it out on your own, search up some stuff. A hint is it's definitely showed up in my slides. And you can try to search up online tools if you want, if you like. It's encouraged. So we're going to come back at 6:23. Yeah. Sorry. Hey guys, welcome back. Hopefully, sorry, I'll do the demo. So, hopefully, you guys have a chance to try it out yourself. I saw someone has got a flag, but don't submit it in the chat, please. Just submit to our Discord bot Orchid, and then the bot will give you the points, so you can show up on our scoreboard. So for this challenge, knowing that it starts with UC-seg, and then according to our previous slide, we're shifting the letter by a certain amount, so we can figure out how many letters, like how many shifts are there from H to U, and then we can do it for every single letter in the cipher. So one tool I like to use is CyberChef. It's really useful if you have things like this. They have all different tools that helps you in cryptography challenges. Like for example, you can convert from base 64. So this one, so it has another name, which is rod 13. So that's shifting 13 places to the right, and then you'll get a flag. Yay! If you're not sure, and you can just kind of brute force it. So starting from 1, and then you go up, and then until you find something that's more readable. And then here's your flag, and then you can submit this to our Discord bot Orchid, and then you'll get the flag. So come back to the slide. Everyone's good? I'm gonna move on. Yes, rod 13. So how do I know it's rod 13? Because if you go from H to U, so going back here, we know it's starting from U, and then this one is H. So if we look in the ASCII table, U is, I'm not sure if you guys can see this, I'll try to make this larger. So U is right here, 117, and then H is right here, 104. So 117 minus 104 gives you 13. So knowing that there are 13 letters apart. If that's clear, if you need any more explanation, good? So moving, if there's no questions, I'll move on. Substitution cipher, monoalphabetic substitution. So monoalphabetic substitution, mono is 1, alphabetic is alphabet. So monoalphabetic substitution is we substitute one letter to another letter. Simple. So right here we're substituting C to N, R to Q, blah blah blah. Usually you can do this by using a dictionary if you're using Python, and then you can just convert this plain text to this ciphertext. So this is a bit harder to crack, especially if you don't have a lot of text. Like for almost all of the substitution cipher, not all of them, but most of them, you can use frequency analysis tool to decrypt the cipher. So for this one, usually they give you a lot of text that's substituted with different letter, and then you can use that to do the frequency analysis. And there are a lot of tools online that helps you to do that. So funny story from here. I have a fun story for you guys. So I was still in UTCDF, I believe, one time, and they had a challenge on alphabetic substitution. I got most part of it, except for 2 of the letters. And then it ended up is one full letter is shift. I didn't expect that at all. So that's a fun story. Just remember, not only like it can substitute for letters, sometimes it's like symbols or numbers or even like just a key. If you are planning to do CTF after, that's a suggestion. I mean, experience. Okay, so next one, polygraphic substitution. So ultimate form of substitution. So in this one, where instead of substituting one letter for another letter, we're doing substitution block by block. So in this one, so the one right here I'm showing is place their cipher. And so you can see here, like here's a cipher, here's the message. So how does it, let's start from encryption. So how does it encrypt? It first splits the message into groups of 2. And because this is like odd number of letters, we are adding a bogus X at the end to ensure we're doing them like pair by pair. So substitute pair by pair. That's the way to say it. So if they're in the same row, we shift both of them right according to the key table. If they're in the same column, we shift both of them down. And then if none of the above, we shift them to the other side where the other to the column where the other letter is located. So this might be hard to think of without showing you a concrete example. So I made a few slides to show you a concrete example. So for PO, searching them up on the key tables, P is right here. O is right here. We shift them because they're not in the same column or same row. So we shift them to the column where the other letter is located. So for P, we shift it to the column where O is located. That gives us C. And then for O, we shift it to where P is located. And that gives us D. So next pair, so that's LY. LY, so we start from, so they are not in the same column or same row as well. So we just shift to the shift L to where Y's column is, and then shift Y to where L's column is. And then here comes the example of they're in the same column. So in this case, we just shift both of them down. And then so we shift G down, gives us M, R down gives us A. And then AP, same thing as before, they're not in the same column or in the same row. So we shift to where each other's column is. And then here comes to an example where they're in the same row. So because they're in the same row, we shift both of them right. So H goes to I, and then K, oh no, there's no letters on the right. What do? We go back to the front. So that gives us F. I mean, it said HI. Oh, never mind. So HI, so we shift H to I and I to K. But if we're doing it on K, then because there's no letters left, we go to the front. Just in case if you wonder, same thing goes for the column shifting. And here, the last part, C shift to, so this is similar to previous examples. They are not in the same row or in the same column, so we shift them to each other's column. And then this gives us the cipher. So what do we do to decrypt? Well, you just do the opposite. So you can see that it's going from C to P and then X to U. If you want to do it backward, then you can because now we are having P and U as at the end. So to undo this, we just shift each other, like shift U to where P is located, giving us X back, and then shift P to where C is located to give us to the column where U is located to give us C back. If that makes sense.
Any questions?
Any questions here?
Give you like a bit because I think
yeah, there's a delay. Oh, by the way, don't forget to remove your padding X at the end. Okay, I'm not seeing question from the chat. So let's move on to transposition cipher. So transposition cipher arranges letter in a unique way that message is not obvious right away. What does that mean? Let's see an example. So this is real fan cipher. I'm usually like this part is not seeable, so I'm putting this out for you guys to see more clearly, but usually you're given the cipher like this. So what is this IEPRLB thing? Is it a rod 13? No. Is this a substitution cipher? No. It's a real fan cipher. So in real fan cipher, you create a rail, so like this, and then you put letters in a zigzag manner. Then you gather all the letters in the first row, all the letters in the second row, and all the letters in the third row, and put them together to give you this cramp of stuff, which it doesn't seem too obvious that it's a I love cryptography in the first sight. So for this type of the challenge, usually we need to recreate the cipher in the way that it is formed. So like for this one, we create the fence, like real fence first. Oh, by the way, an interesting fact is that each row has exactly the same number of letters as the cipher. So, and then we can create a fence using like this fact. So there's a so I think Geeks has a full algorithm, full code on how to recreate this real fence cipher. So I'm not going to cover this here. I don't want it to be too heavy on your brains, especially this is Monday night at like 6-ish p.m. So I'm trying to make this fun and easy on you guys. So you recreate this row and then you put the letters back, then you get the cipher, like you get the plain text. Sounds good. Any questions, concerns, suggestions? I'm going to count down from 5, 4, 3, 2.
There's no need to count.
1. Okay, I'm moving forward. So I'll let Fam do the rest of the presentation for you guys.
To immediately contradict what Christina just said about keeping it easy, we're going into modern cryptography, right? Now, you might have been able to do some of those ciphers. Are the slides not up?
Let's see. I'll stop my screen sharing and then Fam, you can go ahead.
Right. Let me just.
Sorry guys, we're still trying to learn how to work with StreamYard and everything.
Right.
Go ahead.
Let's to immediately contradict what Christina was just saying about keeping it easy and simple for you guys. We're gonna go and move on to modern cryptography. Now, whereas you could have probably done stuff with classical ciphers on a pen and paper, right? This is what we made the computers do to outsmart us, right? So just to hit you with a brick on the head to begin with, we're going with hashing algorithms, right? Now, if there's anyone in the chat that can tell me the difference between a normal encryption algorithm and a hashing algorithm, right? I would love to hear it. Right? It's literally on screen, but let's see if someone can tell me why that's different. Just gonna pause for a second. The 30-second delay.
Anyone is brave enough to shout out your answer? It's alright to get wrong. It's more important that you participate.
All right. If there is no one, right, then I'll just go ahead and say the difference between them is mainly that hashing is a one-way algorithm. It's a one-way function that cannot be reversed. So whereas you can normally decrypt some of these ciphers that we gave you, right? Okay, hashing does not have any apparent vulnerabilities to begin with, but we'll get into its major flaws, right? Now, hashing takes a message and pads it, right, and splits it into certain angles. Now, not since we don't really want you to, I guess, hash something by hand, okay, but it's really good to know what happens inside of a hash, okay. We just want you to understand that, like, hashing, okay, will take a message and spit out this massive hash digest, right? Okay, unique to whichever hash function was used, be it SHA-256 or MD5, right? These are this is the result similar to the results that you might be getting from a hash function, right? Hashing is normally used on passwords, right? Right now, and the reason for that is that it's very, very hard to break. Do we still have that slide? Oh, yes, because it's very, very hard to break most hash functions, right? Most of the time, what you would need to do is do a sort of, how do you say, uh, what was it called? Brute force attack, right? Okay, where you would create a dictionary that maps the hash digit to a plain text, right? This is called the rainbow table attack, right? And this is where you would get a collision, right? Okay, collisions and hash functions dictate that these functions should no longer be used in modern cryptography since, well, it's broken and now you can easily decrypt it, right? Okay, it's still gonna be a one-way function, but the fact that we can find the collision kind of makes it a lot more insecure, right? And from then on, right, we're just gonna move to you trying out a couple of hash digests, right? Now, I just told you that it's gonna be genuinely hard to do this by hand since you literally can't, right? I would. It would be much easier, right? It would be much easier to use a tool, right? Okay. You guys have how long? 5, 10 minutes?
Let's give them 10 minutes.
10 minutes. Uh, I think that's too much since you're gonna be using it too. But like, right?
You're leaking too much information out
Send
there,
them in the
man.
chat real quick.
Okay, I'll
Yeah.
try. I'll send them to the chat.
Yeah. And if anyone has any questions about something that we've presented on, something that's not clear, please
Let us
go
know.
ahead and let us know. Hide it. Hide it.
Huh?
Yeah, okay. Yeah, I mean, that's pretty much what I was saying earlier. Right? Hashing is not encryption, right? Okay, maybe I was using the words a bit too uh, too convertibly or whatever, right? Like, but yeah, hashing is not encryption. It is a one-way function, whereas encryption is a two-way function. That's what we were trying to get an answer out of you guys earlier.
Yeah, and also I would like to share some fun stuff. So, do you have the slides?
Mhm, yeah. What
Yeah.
about these things?
So if we go back to the previous one, so to make this more clear, not all the hash functions have initial vector. I I was a little bit confused, and then I searched it up while making this graph, and then so some hash function like hmag actually uses initial vector, but initial vector is usually more commonly seen uh, in like AES 256, but it's also sometimes used in hash function. But the most important thing about hash is during this process, some information are lost, so it's one way, so you cannot go back the other way. That's something to stress. Good that you know hash is not encryption. It's a one-way function. That's correct. So good job.
Right. I hope most of you got it. Shouldn't have been too hard. Right.
I need to go over the demo.
All right.
How dare you skip it?
Sure, go
It's my
ahead.
demo time.
Sorry.
Okay. So
So
I'm going to.
to
It's not the
it's not the
time yet.
time yet.
We're
We're
giving them 10 minutes, so it's like 51.
If you're getting it,
but,
let us know. Give us a thumb up, give us a comment, say it's good. Then we can move on to the next part. And if you need more time, we'll let you go, keep going until like 6:51. So that's 10 minutes, as we previously said. Right? No, you guys are all smart people, so go for it.
I'm done.
Ooh, good job.
Yay, Gary, let's go.
Let's go, Gary. Oh, Kiwi.
Kiwi.
Victor, yay, good job. Thumbs up. I'm seeing a lot of thumbs up.
I think that now you could demo if you want.
So anyone needs more time? Type in some chat if you. Yeah, you got this from our our how do you pronounce this? Our Nofi. I'm sorry if I pronounced this wrong. Good job, Graceland. We'll go over it, so don't worry if you're not sure if you did it right. Goodbye. Okay, looks like no one is asking for more time. So I'm going to share my screen and we're going to do the demo. Here. So for this one, we can go search up Hashcracker online. And then you can see the first website. It's called Crack Station. Sounds like a fancy website. So let's try that. Yeah.
So if you're a command line person, you can also do it using #cat. I think it's MD5 if I'm not mistaken. But here, yeah. So these ones are actually from some real password that I find in rock.txt, rocku.txt. So that's a leaked public database of password that other people have been using in the past. So for the flag, you just put these all word together, chaining them with underscore, and then adding the UC-seg brackets. So I'll do that. Let me pull up Notepad. So password. So let's start from UC-seg password secured. So secured. That's so easy to crack. What an iron. Also, question: without a hash cracker, how do you know it is an MD5? Well, this is a tough question. You just have to try it out, I guess. Sometimes you also can tell from the length of it. So if it's 256, like for example, SHA-256, usually 256 bits in length. But sometimes you just have to try it out. Yeah, you also assume because it's common, so you try those out first. And also, here's a flag. If you guys want to submit it to ORCID, I'll give you guys a second for that. Then we'll keep on his presentation shortly after.
Right. But yeah, that's good instinct on you. If you if you want to hop on some CDFs, assuming stuff like that, 'cause it's always the assumptions that will get you what you want. Right. Okay. Now for symmetric key algorithm. This is pretty much using the same exact key on both sides in order to, I guess, decrypt and encrypt. Right. Otherwise, sometimes known as one-time password or PAD. Right. This is I guess simpler than it looks, right? Pretty much you take the message to the power of the key, right? And that's what gets you the cipher. And this cipher to the power of the key again gets you the message. You can see why it's the one-time pad, because the key is the most important part. Now, how do we decrypt something like that? Well, that's an XOR algorithm. The vulnerability in something like this is the key being used more than once. That's why it's called a one-time pad. You really don't want it to be used more than once, because if you can find out the message of either one of them, we can use XOR operations to find the key, right? So that's why the key you only want to use it once, right? Okay, is that a question?
It's an answer. So anything identifies internal character symbols like SHA-1, etc.
Mm-hmm.
Yeah, sometimes it's the case.
Right. Go ahead and demo.
Come on, man.
This is.
All right,
By the
great.
way, again, any questions?
So, excellent version right here. So we really just wanna have some fun. Don't want to get into coding stuff. Let's pull our calculator on Windows machine. For those Linux people, sorry for you guys to have to see this, but
Go to your actual calculator.
let's hide this first so you guys not seeing all this crap. I've opening too much stuff on my laptop.
And we wonder why it's burning up.
No wonder why it's burning up. Yeah. So here, if you go, usually you're in the scientific mode. So if you're going to the three open navigation right here, so the three lines, whatever you call it, you click here, and then you can change it to programmer mode. Then you can start playing with it. So you can enter decimal right here. But for this case especially, we're trying to see it from the binary section to see how fun it is. So XOR is like if they're same, they eliminate each other. If they're different, then they keep the one. So let's see. Let's say one bitwise OR with one. What do you get? Ah, that's too much ones. Go back here. What do you get? 0, because it cancels out with itself. And then let's do 0 XOR with 0. You get 0 because they are the same. So you always get 0 when they're when you're XORing the same stuff. What about XORing 1 with 0? You get 1. And if you XOR 0 with 1, you get 1. So that's XOR. The order doesn't matter. So if there's like 1 and there's 0, then XORing them together always gives you 1. And if there's 0 and 0, or like 1 and 1, so if they're the same, then you get 0 back.
Hey, Grace got it. Hey.
Good job, Grace. So something more is, say, if you XOR 111 with 101, you get this stuff. But you XOR it with 101 again. Let's see what happens. So if you XOR it with 101 again, guess what? You get 111 back. So because 101, by XORing it twice, we're canceling out 101 part, so leaving us 111 from the beginning. So that's something to keep in mind for your next challenge.
And
I'll pull this off.
And I genuinely hope you've been focusing, right? Because we're about to do it right now. Right? Now, again, online XOR tools are available, right? And both of these messages are encrypted in hex. Okay. Can we just paste them in the chat?
Yeah, I'll post them in the chat for you guys. So you guys don't have to do the work. So message 1.
Now, this could take them actually a while, so 10 minutes is warranted.
Yeah.
It's all good. Okay. And again, any questions, any concerns, right? Even any corrections if we've been saying something wrong.
Yeah.
Please go right ahead.
Oh, Gary has a question. Go
Okay.
ahead, Gary.
I think you clicked something. Yeah.
Oh, did I?
Alright. Alright. Okay.
Sorry guys, I'm not quite sure how to use this yet.
Okay, so if everybody's done, or if you guys need a little bit of time, please feel free to say. Otherwise, we will be going on with the demo of this challenge.
So, as I have said, it's a Monday night. I don't want you guys to stress too much on the challenge, so I gave you guys this link. So something you can. Am I?
You're not on the stream.
Oh, I'm not on the stream.
Yeah,
Ah,
just stream.
wait. Sorry, guys. Let me put that. Thank you, Fam, for showing me that I'm not on the stream. Okay, here we go. So to make it easier for you guys, on Monday night at 7 now, I have linked this XOR calculator for you guys. So remember what we have experimented before? If we put something here, and we know one of the message is the same as I love cryptography so much, then we can XOR them together. Not knowing which one is the one, but XORing something twice will cancel it out, leaving us the message. So we'll just do that here. Calculate XOR, copy this value, then put it back again. This time XORing with the second message. So we know one of them is a flag. So let's see which one of them is a flag. And then let's see the S key and calculate XOR. Here is your flag. So just XORing all of them together, then you get the flag.
Whoa, let's go.
Let's go.
And I think some people actually got it before we demo.
I wonder if anyone like figured this out before we demo it. Any smart.
We'll give you a shout out if you.
Yeah, we'll give you a shout out if you did it before the demo. We'll trust you. Even if you figure it out after the demo, we still trust you.
Right. Yeah. Now let's go back in. Right.
Yeah.
Hey, Grace. Hey.
Good job, Grace.
Hey.
Wait, so did Grace get the shout out? Let's hope. Okay. So, asymmetric key algorithms. So there is a public key and a private key. Messages are encrypted with public key, and you decrypt using your own private key, right? But how? Okay. So y'all remember modular? Damn. Y'all remember modular?
Calm down.
Y'all remember modular arithmetic, right? Okay, which is pretty much you divide something and you have a remainder, right? So you take the remainder of something. For example, 5 divided by 3 equals 1. The remainder is 2, right? So 5 modulus 3 equals 2, right? Hopefully we're all clear on that. If someone wants to tell me what's 9 modulus 10, right? Okay. This delay. We'll wait a bit for you guys to get the modulus calculators out there because you're gonna need it really soon.
Wolfram Alpha is a pretty good one. Hint, hint.
Right then. Okay. Since 9 modulus 10 is impossible to calculate.
No, it is.
Yeah.
It's like 0 times 10, and then plus 9.
I know, but no one's replying.
Oh,
We're just waiting.
okay.
We just wanna just
What are you doing? Seriously, I'm to check on the account.
shut up. Right? So 9 about 10 is 9.
Yes.
Yeah.
Gaming got it.
Let's go. Hey.
Yay.
Right. Okay. is going to be a bit complex. Diffie-Hellman, if anyone recognizes the man, right? Okay. So we have a public piece G and modular P, right? And they are shared where P is a prime number. Okay. Now Alice and Bob each hold a key of their own. Let's call it key A for Alice's key and key B for Bob's key, right? Alice sends G to the power of A mod P, right, to Bob, right? And Bob sends G to the power of B mod P to Alice, right? Alice encrypts Bob's message, right, with her secret key A to get G to the power of B A mod P, right? And Bob encrypts Alice's message, G to the power of A mod P, using his secret key B to get G to the power of AB mod P, right? Okay. So now we know that technically they have the same key, right? This can be used for algorithms like AES. Can you enlighten us a bit more on AES again? I so forgot to do that. Right.
So AES, if you search it up on Wikipedia, let me search it out really quick.
No, it's all right. We're fine. We're fine.
AES, come on. Advanced Encryption Standard.
Right. Advanced encryption standard. Okay.
You,
Right.
yes, search it up on Wikipedia.
Okay.
You have everything
Okay.
here.
Now we're gonna have. It's gonna be a lot easier for you guys to do this challenge if we have two slides open, right? So if you guys can give us a second, right? Let me just. Just one second slide. I'm just gonna set it up real quick.
Are you able to hide the? Okay, that works.
Right. Oh, I'm gonna go back.
Sorry guys, it's taking a bit long. I'm trying to
Right.
share the.
So
this is very
hopefully it's clear for everyone. Okay. And
copy
we'll
the
quickly
link.
copy and paste it into the chat. Right. Knowing what we know about the algorithm we just shared with you guys, okay, we want you to solve the challenge. Right. So figure out the shared key.
And also shout out to Aegis for making this challenge.
Yeah. Let's go, Aegis.
Thank you, Aegis. Hopefully that doesn't look too bad.
Okay.
The formatting is bad. The formatting.
This might take you a bit, and if you guys have any questions, please don't hesitate. Right? Okay. Again, if you guys have any questions, right, require any hints, anything, or even get lost in the process, we can run through it one more time, right? Just don't stay lost alone. We're here to do this together.
So just a hint, this flag is not a readable format. So sometimes in CTF, there are some flags like this. So it's just a number. So if you get it, there's a hint. The flag is starting with 2, 9, and then the rest of it you have to figure it out. Yeah, good luck. If you guys are getting it, let us know. Give us a thumb up. Give us a comment so we know when to move on. All right. All right, I hope you guys are not struggling too much on this challenge. This one is a hard one. It's not easy. It's all right. It's definitely okay if you didn't get the flag. I didn't get the flag while I was watching Ethan's work. I mean, not Ethan, like EJ's workshop. So it's totally okay if you guys didn't get the flag. But if you get the flag, give me a sound love. I'll give you a shout out. Great job. And I'll do the demo right now. So if you guys are curious, gonna present my screen. Oh, am I? Oh, I'm not. Wait, what? I have two. Ah, here. Screen, entire screen. Okay, here's my screen. So back to the question. We have so from the workshop, we know Diffie-Hellman is like this is the result we want to get to. So this is a shared key. So Diffie-Hellman is a secure way to exchange key, even though like there might be a hacker listening in the middle, hijacking what they're sending each other. But as long as they do not know the secret key, he cannot get the final key that they're using. So that's good. However, in this challenge, one of our secret keys got leaked. Oh no! So now the hacker can use this information and along with boss message and the prime to get the final key they're sharing with each other, and then the hacker can hijack and listen to the message, eavesdrop on the message, which is not good. But here we're on the hacker role, so this is good for us. So pull up your Wolfram Alpha, the powerful mathematic tool. So first, we take this number, and then if we raise it to the power of a, so by the way, this is raising it to the power of b, just to clarify, because sometimes in Python, if you see this symbol, this means XOR. So just to clarify, and if we raise it to the power of a, and then we mod, so take the remainder of the previous number divided by this prime. Here it is. Mod. Then here is our flag. So wrapping this around in UC-sec, points. If you want to do that with the ORCID board, do it right now. If not, I'll tell you a trick. So I used to watch recordings online, and then I just pause the video and then copy down the flag and submit it to ORCID board. But that still works. Anyways, yeah. So here's your last challenge, and here's your flag. Do we have something more? Yeah. So other resource. There's a lot of stuff in cryptography, and it takes a lot of time if you want to go through all of them. There's many interesting topics. Sometimes it's even involved in like what is called, like if you good point. So
Thank you, Amir. That's a really good point.
Thank you, Amir. So using Euler's algorithm, I'm not quite sure what that is. Let's search it up. Euler's algorithm. Oh, is it for the common divisor? Yeah, there is common divisor. Okay. Euclidean. You mean Euclidean algorithm?
Euler's theorem.
Euler's theorem. Yeah. So a to the power of p of n equals 1 mod n. How would it apply here?
I see.
N.
Okay.
Okay, so I'll get back to that. See what this. Anyways, so sorry for keeping you guys for so long. It's Monday night. I know you guys probably have a lot of assignments due or like a lot of midterms. I have 2 midterms and 1 writing composition and 1 assignment due this week. Wish me good luck. Thank you guys for staying with us. Hopefully you learned something. If you want to learn more about cryptography, in U Calgary, you have Math 318 and Computer Science 418. Both are on a great course on cryptography. I will be taking them hopefully next semester or sometime later on in my degree. And in our YouTube channel, our senior or the ex-officials have also made a lot of workshops on cryptography, and they covered different stuff like RSA that we didn't have time to get to. RSA is really useful and it shows up in a lot of CTF challenges, so be sure to take a look. Also, I remember he just also did a veneer cipher in his previous workshop, so that's a good thing. That's a substitution cipher to know, good to have in your pocket as well. But due to time limit, we didn't have time to cover all of this. Also, we want to make some fresh content for you guys, so you guys, if you're coming back, you don't get bored. And thank you guys for coming. And here's a reference that I didn't know many of them until I started searching it up online. So give credit to those people. And here's the attendance sheet if you didn't have time to fill it out. Again, thank you guys for coming.
Hope you guys had a good reading week.
Yeah, hope you guys had a good reading week. How's your reading week? Tell me in your comments.
Where everyone's free to leave.
Also, I want to switch up this
You guys can
0.
make sure you've submitted the flags. Automatic says he's been busy. Is that out to me? Yeah.
Thank you guys for coming. Thank you. You guys being here is like the greatest support for us. Like, it's really happy that like we see people are seeing our work. Like, yeah.
Not long enough. What you mean, Kiwi? Okay. Right. Hopefully we didn't take too much of your guys' time.
Yeah.
Kiwi, you're free to stay. And yeah.
And by the way, my binary exploitation workshop will coming up 2 weeks later, I think. And this is reverse engineering workshop will come up next week, I remember. So be sure to take a look at the comp here. Reading week was always I know, right? I want to take more break. Who the hell? I should not be swearing. Who knows that I have to week and when I'm writing composition?
Okay, it's okay. It's okay. Thank you guys so much for coming out. Right. And hopefully we get to see you next Monday, right? Next Monday for our next workshop. Right? Who's it with? Whoever they are. Right.
Yeah, and also, do we have challenges of the week today? I don't know.
Good luck on your guys' midterms. If you have anything after reading week, and hopefully
my midterm go well as well.
All right. See you.
See you guys. Have fun.